Now we are going to look at some of the special cases which are related to finding out the magnetic field at a point. Now, so for example, like as we have seen that there was a coil, right? And on that coil we needed to find out the magnetic field intensity at a point which is located on its axis of the coil, of the circular loop or the coil. Now we found out the expression for B at that position, B on axis of a coil. We found out the expression as mu naught I r square divided by 2 multiplied by r square plus x square to the power 3 by 2. Now what was r square? R was the radius of that coil or the circular coil, and x was the distance from the center of the lobe plane to the point where this B is actually measured, right? We could modify this equation also like mu naught I multiplied by pi r square. We have multiplied on the numerator side with pi, so we must multiply on the denominator side by pi as well. So 2 pi, it is r square plus x square to the power 3 by 2, right? So we can write this expression now as mu naught I A divided by 2 pi multiplied by r square plus x square to the power 3 by 2, right? Now over here, if we say that this, say for example, now we take that R is very lesser than X, then this R square could be ignored in comparison to X square, right? So we will get the entire expression now as equal to mu naught I A divided by 2 pi multiplied by x cubed, where A is equal to area of the plane of coil, right? That, like say for example, this one was the coil, this one was the radius, so the area of the plane of the coil would be equals to A, which is equals to pi r square, as we know that the area of the circle is equals to pi r square. Now this is B, right? Equating, or just like not equating, or by considering or comparing with the equation of electric field, we can say that the electric field that was found out was equals to E equals to 1 divided by 4 pi epsilon naught multiplied by divided by r cube, or we can write it as x cube. Now, as we have seen in electrostatics, that this expression was for which thing? Yes, for a dipole moment. But on the axis, likewise, we have found out this B. For on the axis of this current carrying coil, right? If we could remember about this E, let us recapitulate that there was a minus Q, there was a plus Q, there was a dipole moment. The P over here represents the dipole moment, and there was something, a point over here on the axis, which means that this Q and plus Q, these charges, they were on the same straight line as this point was. So the distance of this point from over this point was equals to x. At that point of time, we did find out that the electric field was equals to 1 divided by 4 pi epsilon naught multiplied by 2p divided by x cube, right? Now, equating this very same, we can write that B is equals to this one. We can take it as mu naught divided by 2 pi, or now we can say that mu naught divided by 4 pi. We have multiplied by 2 on the denominator side. Now we need to multiply by 2 on the numerator side as well. 2ia divided by x cubed. And comparing it with the same terms as E, that was equal to 1 divided by 4 pi epsilon naught multiplied by 2 times the dipole moment in this situation divided by x cubed. Now observe closely. This thing is a constant value. Likewise, this is also a constant value. We have got x cube over here. Likewise, x cube is also present over here. Right? And we have found out this 2 and this 2 over here. The only remaining comparison is that, like, the product of the I and A, I mean the product of the current and the area of this coil plane is similar as that we got for the dipole moment. So if we introduce the term, this is the dipole moment of what? The electric dipole moment, right? Likewise, now if we do introduce that for a magnetic dipole moment, magnetic dipole moment, which could be represented as capital M, then it would be equals to, because with the left out comparison is only P, which is the electric dipole moment, right? And over here we could say IA. So we could state this IA as the magnetic dipole moment. So the magnetic dipole moment, it could be stated as the product of the amount of current flowing through this coil multiplied by the area of the plane of this circular lobe, right? Now, as we have seen in the case of the solenoid as well, let us check some special cases. Over there in the solenoid, we did found out that over there B was equals to 1 by 2 mu naught Ni, where N was the number of turns per unit length multiplied by cos phi 1 minus cos phi 2, right? Where it extends from phi 1 to phi 2. Now, first case, if we do take the case of an infinitely long solenoid, try to think of the situation of the solenoid in the previous lecture, and you will find out that over there, this was, say for example, this is, we have seen over there phi 1 and phi 2. Say for example, this one, this line indicated the phi 1 where the angle was on this side, and phi 2 where the angle was from the entire, from this to the entire, right? Now, if it becomes an infinitely long solenoid, this will turn out to be 0. And this will also go like this. This will turn out to be 180 degree. For green it will be 0, for blue it will be 180 degree. Right? Why? Because we have seen over there that if this was the case for the solenoid did actually stretch from this point to this point. Over there, this was phi 1, and this was equals to phi 2. Now if we extend this till infinity, we will see the decrease in phi 1 now, right? So over in this case, the phi 1 will become 0, and if we increase this over this point till infinity, we will see an increase in phi 2. So now the phi 2 shall be equal to 180 degree or pi, right? Now putting these values over in this equation, we shall get it as B will be equals to half mu naught N multiplied by I. This is cos phi 1, right? So cos of 0, which is equals to 1, minus the cos of 180 degree is equal to minus 1. Likewise. So this negative and negative will actually be positive, so it will be 1 plus 1, that is 2, and that 2 will actually cancel out this 2, right? So we will get that B is equals to mu naught N multiplied by I. Okay. Now let us check the case, the second case, that if the observing point is at one end of an infinitely long solenoid. The first case was that our observation point, or the point from where we are observing, that is well inside the solenoid. Now the second case is that the solenoid is again infinitely long, but now our observing point is either at one end, at this end, or at this end, at one end, right? So over there we can say, in this situation, the phi 1, if we are, say for example, on the left hand side, this phi 1 will simply be equals to pi by 2, because if we are at this point, at this end, we will simply drag up this line, and this line now will be equals to pi by 2, right? So the phi 1 will turn out to be pi by 2 if we are on this end. So the phi 1 will turn out to be pi by 2, right? And the phi 2 will be equals to, this will go likewise, right? This will be equals to 180 degree or pi, right? So deducing this thing, because see, this will be over here, it will go like this, the angle, this was only phi by 2, now the phi by 2 is increasing, so the phi by 2 is now equals to pi. So now we can write, putting this phi 1 and phi 2 in this equation of B as B is equals to 1 by 2 mu naught Ni multiplied by cos of phi 1 or cos of pi by 2. What is it? Simply 0. Minus cos of 180 degree of pi. What is the value? It is simply equals to minus 1. Minus 1. So this minus and minus will cancel out to be positive. So we will find out the expression for B as 1 by 2 mu naught Ni. Now, as it was told earlier, that if we do find out in any case that these situations or these scenarios are not in free space or in vacuum, or they are not in air, then we simply need to change all this mu naught into mu, such that we know that mu is equals to mu naught multiplied by mu r, where mu r is known as the relative permeability. This mu r is basically known as relative permeability. Right? So this is all about the special cases or the special scenarios of the solenoid cases, and we have understood now that what actually the magnetic dipole moment is, and we have also found out the expression for the magnetic dipole moment as it is a product of the current that has been carried in the conductor multiplied by the area of this coil, the plane, right? The area of the plane of this coil. Thank you.